Let's think about the simple harmonic oscillator, SHO, and let's find the potential for the simple harmonic oscillator and then look for solutions of the Schrodinger equation with that potential and see what the system looks like quantum mechanically. So classically, we know that we have F equals minus kx if we allow the oscillator to stretch in the x direction, so x represents the stretching of the oscillator. This is minus the gradient of a potential, and so that potential is a function of x. And in one dimension, this looks like minus dv by dx I hat, and then of course that gives us minus kx I hat. So when we integrate this, right, we integrate the force over some distance x, we'll get the potential, and that potential is 1/2 k times x squared. Of course, we can write the constant k, the spring constant, in terms of, oftentimes we'll see this in terms of the angular frequency, omega naught, and the mass of the object that's attached to the spring as k over the mass square root. Right, where does that come from? So if the force is, we're in one dimension and the force is minus kx, if we just look at, well, it looks like that, but we know that the oscillator, if we plot the oscillator, so we stretch it, so this is the amplitude of the oscillation, we stretch it to some value x naught in the x direction. Sorry, this is time, and this is actually x. X is a function of time, and so we start at a value x, x naught, and we let the spring oscillate. It'll oscillate back to 0. It'll oscillate down to negative x naught. This is the classical behavior, and so on. It will continue to behave like that if it conserves energy. So we know that the position is given by x naught cosine of the frequency that I called omega naught t, right? The phi here is 0. Our initial condition is such that at t equals 0, the displacement is x naught. So this is the solution to that. Let's take two derivatives of this. So two derivatives of x in time. That'll give us minus omega naught squared times x naught cosine omega naught t, and that's minus omega naught squared times x itself. So we have, if we think of ma equals f, then we have m times this acceleration, which is minus omega naught squared x, equals minus kx, because that's the force. And so we get that k is equal to m omega naught squared, and so follows is this, which is omega naught is equal to k over m square root. Okay, so that's that relationship. So we want to put this potential into the Schrodinger equation and explore the solution. So let's write the Schrodinger equation here. Okay, we have minus h bar squared over 2m, or the time-independent Schrodinger equation. Right, so these are discrete functions. These are the eigenfunctions of energy. We have plus 1/2 kx squared. 1/2, if we write in terms of mass and angular frequency, we have 1/2 m omega naught squared x squared times psi, and that's equal to e psi. And so the bending of the wave function is governed by, right, the two derivatives of psi and x is given by 2m over h bar squared times m omega naught squared x squared over 2 minus e times psi. So when we look at this, this difference can have positive or negative values depending on the value of x. So if we're further enough away from the origin, then this term will dominate, and all of this will become positive. And so we have some kind of exponential decay-like solution. It's not going to be like the finite well, because the difference between this and this increases more in this case as x gets larger. But it's e to the minus something. Whereas if this is small enough, then this term dominates, or at least is larger than this term, then we get negative. And so we know that the bending in that case is toward the x-axis. So we'll build our solutions by looking at this in more detail.